Hey everyone, this video takes a slightly different look at titration. What happens if when we're titrating we have what's called a diprotic acid, or in the case of if we were to titrate Coca-Cola, phosphoric acid is triprotic. Well, because H2SO3 is a weak acid, we would expect our titration curve with pH on our y-axis and our volume of NaOH, or effectively, OH minus ions on the x-axis, to look something like this. Well, if we were to say that, 7 is about here, because this is a weak acid, H2SO3 is sulfurous acid, we would expect, if this were a pH of 2 down here, it wouldn't really start down at 0 or 1, but maybe just a little bit above or below 2. So we're not just ripping off one proton, as in the case of, for example, HCl, but when we look at H2SO3, we're actually going to be ripping off 2 protons. And because H2SO3 is a weak acid, both of those protons are generally still on the H2SO3, even when it's just sitting in water. So what we're going to draw is a curve which looks a little bit like this. And unlike our previous curves, where we had a single jump, we're now going to actually have 2 jumps. And instead of just 1 equivalence point, we actually have 2 equivalence points. And those correspond to the hydroxide taking off each of those H atoms and making 2 waters each, well, 1 water each time, for a total of 2 waters. So just to sort of look at this beforehand, really what we're doing is, if we were to look at the entire reaction as one reaction, and if I were to write this in net ionic form, I would show both hydrogens still on the H2SO3 because it is a weak acid. However, the sodium really is a spectator ion, so it's not important that I write the sodium if I'm really looking at this from net ionic, or what's really happening, terms. And on the AP exam, they often have you look at the net ionic. If we were to write it in the total molecular form, of course, we would show the sodiums. Now, the reason I wrote a 2, right, is because 2 equivalents, or 2 moles of hydroxide, are going to be needed to react away both of these hydrogen ions. So instead of making 1 water, I'm in fact making 2 waters, and what's left over is the SO3 2 minus the sulfite ion. Now this is the overall balanced equation, but when doing a titration, this doesn't happen all at once. And in fact, only one of those protons comes off first. So the reason why there's 2 humps and there's 2 stages really is because H2SO3 reacts first with just 1 equivalent, or 1 mole, of hydroxide. And the first complete substance made is 1 water and HSO3 minus 1, what's called the hydrogen sulfite ion. This reaction happens in completion before this second proton is ripped off by the hydroxide. So, whoops, that's a 3. The reason why we have 2 humps is because there really are 2 steps in this process. H2O and SO3, 2 negative. And what you would notice is, if we were to sum these two, what we would end up getting is, in fact, this overall reaction here. So now that we know what we're looking at, let's go back up front. If I were to label different parts of this graph, I could say that I'm going to say this is A here, and I'm going to call B the half equivalence point, C the equivalence point for my first titration in my first proton, D right here, and E here. And I could start to take a look at what the different species are. At point A, I pretty much have all HSO3. Because this is a weak acid, it's a scenario where most of those protons are still on that because we haven't added any base yet. This is just H2SO3 sitting in water. And point C is our first equivalence point when all of them have been converted to HSO3 negative. And point E, our second equivalence point, is when we have, no H's there. All of these have been converted to SO3 2-. So what about B and D? Point B is what's known as the half equivalence point. And at this point, the concentration of the original H2SO3 is equal to the concentration of HSO3 negative, meaning at point B, that is when half of these H2SO3s have been reacted away. And I have equal moles and equal molarity of H2SO3 and HSO3 negative. And then, of course, part D is in fact the half equivalence point for a situation in which the HSO3 negative moles and molarity are equal to the SO3 2 negative molarity, meaning half of the HSO3 negative, half of the hydrogen sulfite ions have been converted to the SO3 2-, the sulfite ions. And one more point I would like to make is because H2SO3 has in fact 2 protons, if we scoot over and we take whatever point B is and we go over to the y-axis, this point over here is the pKa of the first proton coming off, and D, if we extend this line all the way over, this point here is the pKa of the second proton coming off. I know Sohan explained that in the previous video for monoprotic acids, and now here we have for diprotic acids.